Hello, I'll be presenting fast database joins and PSI for secret shared data. It's a joint work with Mike Roselek at OSU and Payman Mahaso, who's now at Facebook. So private set intersection refers typically refers to the problem where you have two sets, X and Y, and you wish to identify the items which are in the intersection here, but you don't want to reveal items that are outside the intersection to either party. So in this case, Bob shouldn't learn the items that Alice contributes, which are not in the intersection, and vice versa. But this problem's been around for a while, and we want to sort of spice it up. So we consider a richer set of functionality. I'll describe next. So we don't just want to solve the PSI problem. We want to solve many of the sort of more general database joining type problems. And so shown here, PSI is sort of in the top left, but we might want to do other types of joins in addition. And from a security perspective, it doesn't quite make sense to consider these other types of joins unless the output is itself a secret shared. Because, like, say for a left join where Alice's whole set is in the output, then she could simply reveal her set in this interaction. And so what we're going to do is actually require that the output of the join, depending on what type of join it is itself a secret shared among the parties. So that's shown here as they are blindfolded, implying that they don't actually see what the output data is. And in fact, we're going to go one step further and require that the input to the protocol itself is itself secret shared. So the parties don't know anything about the data, the tables or the sets that are being joined, apart from the fact that there's some upper bound on the number of rows that are in the given table. So yeah, they don't know what they do. And in fact, we will additionally allow you to do key value pair joins. I won't really get into this, but this basically allows you to get a large section of sort of SQL style join operations where everything is secret shared among the parties. We'll consider this semi-honest setting. We'll actually have three parties, not just two, as I shown in the example before. But since all the data is secret shared, this doesn't really change the logical setting. And we'll also consider an honest majority. And the inputs, as I mentioned, can be secret shared. So that means some other external party can provide the inputs. So first I'm going to go over our sort of basic protocol without any security consideration. So don't think about secret sharing or multi-party or anything like that so far. Let's just first nail down exactly what our algorithm is sort of doing. And then we can talk about how to project this into the secret shared setting and PC setting. So the first thing we're going to do is we take the set X, and we're going to do this thing called cuckoo hashing. That's sort of a common technique. And cuckoo hashing works is that each X can live at two locations, and the two locations are specified by these hash functions, H1 and H2. And so each X can live at one of these two spots. Which one it picks is sort of a separate question, but one of them gets picked, and that X gets put there. And for all of them, and maybe you'd end up with something like this. Next, we will do on the other side with the set Y, we'll do what's known as simple hashing. So they use the same hash functions, but instead of putting in each Y only one of the spots, we will put it at both locations. I'll show you here. And so you end up with something that looking like this. And since each X will be stored at both locations, we have to allow, or say Y, we have to allow it for more than one item is in at any given position. So that's what this horizontal axis is. And now you can observe that. So here I will use if the x's and y's are the same color, that means they have the same value. And now you can see that for each x, if there's a matching y, then it will be in the corresponding bin, shown here. And so this sort of leads to a natural protocol in that you can sort of compare things row-wise and identify items in the intersection. And, in fact, you can do other operations. But the problem with this is that the number of comparisons that we would have, secure comparisons we'd have to do, ends up being n log n, where n is the size of the set. And this is because we don't know how many y's get mapped to any given location. And so this would not result in a linear overhead protocol, which we'd really like to do. And so what we're going to do is we're going to add another level of indirection. This is the classic computer science trick, right? And so here what we're going to do is we're going to take the hash table that has the x's in it, and we're going to select locations out of it based on the hash values of the y's. So here's y1, and we will map these two values since there's two hash functions, we'll map it to two new tables, one for each of the hash function values. And we'll do this for each of the y's, say y1, y2, and now you can observe that for each, since the same hash function is being used, if there's a matching XY pair, then the corresponding X would have been mapped to one of these two tables at that corresponding row. And so shown here, like this X for the X5, X2, and X4 match. And everywhere else there isn't really a match, but that's okay. And so now observe that there's only actually two comparisons that we need to do. One with the first table on Y and one with the second table on Y. And so we've reduced the number of comparisons that we do to be linear, which is great. So this is sort of our overall protocol. But then we have some security challenges in how you could actually do this. I think this is great for plain text joins, but like how would you do this one over in the secret shared setting? There's sort of several challenges. One is how do you revealing these hash values could leak information about the underlying sets. And so we need to have some way to secure against not leaking the hash values. And then as it turns out, there's some difficulties in rearranging these doing these permutations, these mappings, where you shuffle the items around. How to securely do the shuffles, and how to finally do the comparison. So to get around the issue with viewing hashes of the values, we actually will use a PRF where no one party knows the PRF key, and they'll interactively evaluate the PRF to get the hash values. And then one party learns the hashes for the x's, and the other party learns the hashes for the y's. And so by doing it this way, I won't get into details, but you can maintain security. And then the next step is how do we do this mapping thing? And to achieve this, we use this notion known as oblivious switching networks. And this is basically just sort of the abstraction that we use for how to do this mapping. And here, one party will have the mapping function pi, and then the other parties will have secret shares of the input vector A. And then what will be output is new secret shares of the underlying vector mapped according to pi. So as a warm-up, you can consider permutations where, in general, right, one item can appear more than one spot in the output, but permutations sort of don't allow this, and then each input item appears exactly once in the output. And so you can get a permutation protocol in the honest majority setting by simply secret sharing this permutation in some way, in a functional way, and then having each party apply a part of the permutation. And possibly you don't see how this works. And then to get the overall switching networks, what we'll do is shown here. First, we apply a permutation, which rearranges the input items. And then based on how we rearranged it, we can then see how we can duplicate one item into the next so many slots. And this allows us to duplicate items, get the right multiplicity. And then finally, in a final permutation, we map it back. And then so the question is, how do we do this duplication? And shown here on this slide is sort of a discussion of how it's done. I don't have time to go through it, but it's some sort of protocol that lets you duplicate items as shown here. And so this is our final protocol. And with a tiny bit more work beyond this basic what I showed you, is that you can get joins, inner joins, full joins, left, right, union, you name it, you can do it. We do have some restrictions in that the keys need to be unique that you're joining on, but that's not too big of an issue typically. And in fact, we also get really great performance. There are some protocols, like some classic PSI protocols, which are faster, but they are solving a much simpler problem, so it's not quite fair. But the main point is that we can do like a secret shared PSI in like 5 seconds, or we can do sort of more general joins in 9 seconds for 1 million items. Yep. And conclude and say